Well, good morning, class. This is Mr. Roberts, and I am standing in beautiful room 309 on the Shasta High School campus. And today we are jumping into section 5.2.3. The title is, How Else Can I Write the Equation? And we're going to be learning not about a new kind of sequence, but a new kind of notation for writing down the sequence. It is called recursive notation. So let's have a review of where we've been so far and then jump into where we're going. So far, we've gained an understanding of the idea of a sequence. A sequence is an ordered list of numbers. And when we have an ordered list of numbers, we understand that not only are the values in the list important, but the order that they appear is also important. The sequence 8, -2, 4, 10 can be written in a table. N indicates the term number. The first value that we see will always be our first term. So I have a first, a second, a third, and a fourth term in this sequence. And the ellipse indicates that this continues, ... The values for each of those terms are -8, -2, 4, and 10. And I can see in this sequence that every single time I move forward in the list, I'm adding 6. -8 plus 6 is -2. -2 plus 6 is 4. 4 plus 6 is 10. And because I see that pattern in the values in my sequence, I can extend it. This is an arithmetic sequence because my terms have a common difference. The common difference is 6. And in order to figure out what a common difference is in a sequence, I take any term in the sequence, for example 10, and I subtract from it the term that precedes it, 4. 10 minus 4 equals 6. My common difference is 6. The other type of sequence that we've considered so far is a geometric sequence. A geometric sequence does not have a common difference. We'll learn that it has a common ratio. If I look at this sequence of numbers, I can see that every single time I move forward on the list, I'm simply multiplying by 1/3. 27 times 1/3 is 9. 9 times 1/3 is 3. 3 times 1/3 is 1. 1 times 1/3 is 1/3, and the next value would be 1/9. This is a geometric sequence, and we'll be talking more about it later. When we recognize that we have an arithmetic sequence, we can come up with the explicit equation for this sequence, a way of writing down the value at each term in the sequence given the term number. Pretty much it's exactly what happens with a linear equation. I have a slope of 6, or a common difference of 6. That means every single time I move forward, I'm adding 6 in the list. If I was to write down t of n, that means the value of the sequence at any point n, it equals 6 times n, which is certainly true because I'm using multiplication to show the fact that I am repeatedly adding 6's. The other thing that I need here is my beginning, my 0th term, the value that's not shown in the sequence. To get that, I can take, for example, the first term, and instead of adding 6, I can subtract 6 from it. -8 minus 6 is -14. So my 0th term is -14. So instead of writing plus -14, I'm just going to write minus 14. This is an explicit equation for this sequence. The explicit equation takes as an argument the term number that you would like to know the value of. When we plug that term number into the explicit equation, it gives me exactly the value of that sequence at that point. So for example, if I was to pass an argument of n equals 4 to this explicit rule, I would see that t of 4 equals 6 times that 4 minus 14. 6 times 4 is 24. 24 minus 14 is 10. So we can say that t at 4 is 10. If you know the explicit equation, it's very easy to get values way down the line. You just plug in your value that you're looking for and it tells you. In this chapter, we have been writing equations for arithmetic sequences. Today, we're going to investigate recursive sequences. We just looked at an explicit equation for an arithmetic sequence. Today, we're going to look at recursive definitions for sequences. A term in a recursive sequence depends on the term or terms, it could be 2, 3, or more, that appear before it. Let's continue to think about the sequence -8, -2, 4, 10. So we understand that these terms have values, their locations and values. This is the first term, this is the second term, this is the third term, and this is the fourth term. If I want to talk about a generic term in the sequence, I can say, hey, this is the term t of n. The term that comes immediately after that would be the t of n plus 1 term. So when I look at these, this is any term in the sequence. This is then the term that comes after that term in the sequence. I can write a bridge from the next term in the sequence using the term that I was at. So here's the bridge. I can say that the next term anywhere in this sequence will equal the term that I am currently at plus, in this case, 6 more. So if you think about this, this is part of a recursive definition because it tells me to get to the next term, take the term that you're at and add 6 more. Now I keep saying that and I'll continue to say that because I want you to get used to this notation. This t of n plus 1 equals t of n, that doesn't do anything for my mind anyways. So when I see these, I say the next value in the sequence is equal to the value that I'm at plus 6 more. And I can see the truth of that statement because anywhere in this sequence that I plop down and say this is t of n, for example here, this is t of n, this is t of n plus 1. What I'm saying is that, hey, the next term, if I'm sitting here at the spot 4, I'm saying to get to the next spot, to get to the t of n plus 1 spot, take the value that you're at, the t of n, and add 6 to it. 4, the value that I'm at, plus 6 more, is going to equal the next spot in the sequence. The next spot in the sequence is the spot that you're at plus 4 more. This rule does an excellent job of capturing how growth is occurring in this sequence. The next value in the sequence equals the value that you're currently at plus 6 more. But the problem is that definition applies to a lot of different sequences. So for example, if I was to start with a sequence that began at the number 2 and use this rule, it says in order to get to the next value, take the value that I'm at, 2, and add 6 more. This would become 8 plus 6 more would be 14 plus 6 more would be 20. Plus 6 more is 26. Plus 6 more is 32. Plus 6 more is 38. I don't need to keep going. If I was to start at the number 10 for my sequence, 10 plus 6 is clearly 16. Plus 6 is 22. Plus 6 is 28. Plus 6 is 34. Plus 6 is 40. And it keeps going. So having the recursive rule, this rule that says in order to get to the next value in your sequence, take the value that you're at and add 6 more, that's not enough. It's not enough because it applies to this sequence, this sequence, and this sequence. And if we're trying to describe sequences mathematically, we need a little bit more information so that we all know exactly what sequence we're talking about. To fix this, what we do is we include not only this thing that I'm going to call the recursive rule, but we also need to include a starting point. So to define a sequence recursively, we need two things. Yes, I'm typing. Two things are needed. If we consider our initial sequence again, the two things that we need are, first of all, the recursive rule. Here, the recursive rule would be, in order to get to the next value in the sequence, t of n plus 1, the next value in the sequence equals the value that we're currently at, which is t of n, plus the common difference, 6. Fabulous, but that's not enough. The other thing that we need is a starting value. And in order to share the starting value with the user of our recursive rule, we simply say something like t of, let me do this as an equation, t of 1 equals -8. So if we have both of these together, where we are beginning, and also how do we move forward, we have enough information to write down the sequence. So we now have everything that we need in order to define this sequence recursively. We have both the starting value, our first term is 8, and you can see that we're saying that here very clearly. The first term in the sequence is -8, not 8, Mr. Roberts. And we also show how to move forward in the sequence. Again, in order to get to the next term in the sequence, you take the term that you are at and you increase that number by 6. That works anywhere. If I want to get to the next spot in the sequence, what do? I take the term that I'm at, the last term that I know, and I simply add 6 to that. So together, these two items constitute what we will call the recursive definition of a sequence. Both the recursive rule, that is to say, how do you move forward in the list, and the starting value. If you provide me with both a starting value and the rule about how to move forward, I'll know your entire definition and I'll know your entire sequence. Let's contrast that real quickly in closing with the other way that we can write down the rule for an arithmetic sequence. We can write down the rules for an arithmetic sequence recursively, not recursively, explicitly. So if you remember, this sequence had an explicit definition that was, in order to get anywhere in the sequence, you simply take 6 times the term number that you're looking for, and you subtract, we subtracted 14 minus 14. This does not need me to give a starting value. It doesn't need me to give I don't need to know the term before or the term after. I just need to know, hey, I want to know the 12th term. I can put it in.